Good afternoon. My name is Rich Nass. I am the Executive Vice President of Open Systems Media. I am here with Pim Toyles. He is the founder and CEO of Intrinsic-ID. Good afternoon, Pim. How are you today?
I'm fine. Thanks, Rich, and good to meet you this afternoon.
Same here. So we're here to talk about security as it relates to memory, which is something a little different for me. And I'm going to ask you to explain this to me, because I often wonder about if it's real that you're adding something to the security puzzle, or you're just throwing it in there with all the other security stuff and mixing it up and hoping that it makes the system more secure.
Okay, Rich. Well, thanks for giving us the opportunity to speak here. So what I want to talk about today is how one can secure the Internet of Things with a really new and innovative concept called SRAM PUF. And in order to explain that, I want to start with giving a little bit of a different view on the IoT maybe than most people have been thinking about it. So the Internet of Things, or IoT, is really a very big system that is autonomous, connected, and exponential. And with autonomous, we mean that it is a system that will take decisions without human intervention. So the system is going to sense things, and based on what it senses and its intelligence, it will decide to do something or not to do something. Switch traffic lights on red, for instance. And it can do that because it is also connected, and at the same time, it's growing exponentially. So let me show you some graphs to illustrate this. So in 2019, there were about, let's say, a little bit less than 2 billion PCs, a little bit over 2 billion, close to 3 billion smartphones, and already 8 billion IoT devices. So that's a lot. So what was expected by companies like Gartner and SoftBank is that in this year, 2020, there are about 50 billion IoT devices, and this would grow to about 1 trillion IoT devices by 2035, which is an astronomical number. And that's, of course, all needed to make such an autonomous system that can take its decisions. Now, at the same time, what we see is that, according to a study of Symantec, there is a 600% increase in the device attacks on Internet of Things devices between 2016 and 2017. And that's, of course, a problem. That's a problem because an autonomous system, you have to be able to trust it. And if those things are being attacked, then you're not sure anymore whether it is a trustworthy and genuine system. So let's also dive a little bit deeper in what it means. And in particular, because such an attacker has an unfair advantage. And that might not be realized by many. And that's also why we want to explain this. So let's look at that. So an attacker typically has an unlimited amount of time available. He doesn't have to attack today. He doesn't have to attack tomorrow. He can take his time. While a legitimate manufacturer of devices has a limited amount of time. Its device needs to get on the market by Christmas or by Easter or by Thanksgiving. So that's a fundamental difference. The attacker can take its time. The attacker also can choose where he attacks or when he attacks. While as a legitimate manufacturer, you're again restricted. You have to produce at this site in the world. You have to test your devices at another site in the world. And that's your limitation. You cannot change that. While an attacker, he can attack wherever he wants, in the factory, in the testing house, or even in the field. The attacker typically has an unlimited budget. he is not constrained by the fact that the device costs only $1. He can spend $10 on the attack. He can spend $100, $100,000. He is unlimited. The manufacturer typically has a restricted budget. Yeah, the device can only cost $20 or $10, $100, whatever it is. But you have to do it within that budget. And that also means that if you want to protect your device, you only have a limited budget, yeah, for security measures. The attacker also has an unlimited, let's say, resource amount in terms of power, electricity power, battery power, while your device, a typical IoT device, has low to very low power, one battery, and has to run for 10 to 20 years based on that one battery. And the attacker can choose temperature at which he attacks. He might put your device in the fridge to have let it have a strange behavior, or in an oven. While as a manufacturer, you have to build a device that always works. It has to work in that valley. It has to work in Alaska or in Florida. It always has to work. Yeah. So as a manufacturer, you're faced with a lot of constraints, while as an attacker, you have free choice. And at the same time, as a manufacturer, you have to make sure your device is secure. So if you want to protect the devices in the Internet of Things, you have to dissect your devices. And if you look a little bit inside those devices, what you typically will find these days is a number of chips. Yeah, that's where the intelligence comes from. Yeah, there is Wi-Fi chips typically, or Bluetooth chips. There is a CPU, there is memory, there is a microphone, maybe other sensors. And you see that in voice-assisted devices, you see that in cars these days. So it means that the security has to start there. Yeah, this is like the smallest atomic entity responsible for all the intelligence. So how to do that? Well, on these semiconductor devices, you need what they call secrets. Yeah, because if they have something secret and unique, well, then you can distinguish one device from the other. They can do something that another device cannot do. They can protect something. And therefore, you need to build on those devices what they call a secure key vault. And what is a secure key vault? It's a digital equivalent, if you want, of a mechanism that allows to store secrets securely on the chip or off the chip, as long as it is secure. And we have to make sure that these secrets stay secret or confidential, and that they cannot be replaced, you know, that you're not working with the secrets of an attacker. And typically it's something that will leverage some storage or some kind better of storage on the device. Now, the solution that we will speak about today will create those so-called secrets in terms of cryptographic keys that are derived from a PUF root key, as we will explain. They can be used to encrypt data, to add authentication tags, to verify the authenticity of a digital object, and of data when the data has been decrypted. Now, you might think, doesn't such a solution exist? And indeed, there is a legacy NVM solution on the chip. NVM stands for non-volatile memory. You can think of long-term storage memory on the chip. And typically, what is done is that a secret key, which we show in orange here, is written into a memory on the chip, in a long-term memory on the chip. And while you do that, you see that the key is visible there in the memory, because that's the only thing you can do. Another solution that is sometimes used is to connect another secure element chip, as they call it, yeah, to the original chip, yeah, and that secure element chip is then built to keep secrets, yeah, and to make sure that it can arrange the full security of the system. But there is an interface here between that secure element and the chip, and that interface is typically vulnerable, yeah, for attacks because it's an open interface. And you might still say at first sight, well, why don't we use that one? Well, let's illustrate that with a, I think, nice animation that makes it very clear. So the art really is, how do you keep a secret secret? Yeah, so let's go back to the problem. Let's say this orange key is injected into the chip and written into a memory. So you see here that we show the orange key on the chip. You can imagine it as being in the memory, and we show it in a visible way. Why? Because it is visible. Data in a memory is visible data. Maybe you have to use a microscope to see it, but it is there as a physical state, so it is always visible. This might be surprising to you. It's not, let's say, very well realized by many, but this is the case. There's nothing you can do about it. Usually somebody will say, well, we encrypt that key, and therefore it becomes invisible. Okay, so let's look at that, how you would do that, and how that would work. So let's say we are going to encrypt the orange key with a dark blue key. So we need a dark blue key. We encrypt the orange key. But it also means that if we want to get access now to the orange key, we need the dark blue key to open that lock. So then you see, well, where is the dark blue key? Well, there is no other solution than having it in a memory on the chip, because otherwise it's not available to the chip. But if it is in the memory, it is visible. So you might say, well, but a dark blue key, we make it invisible by encrypting it. So it means you need a light blue key to encrypt the dark blue key. But now the question becomes, how do you get access to the dark blue key that gives you access to the orange key? Well, it means that the light blue key has to be on the chip. So it is in the memory, so it is visible. So you see where this is going. Yeah, you could say now, well, we encrypt the light blue key, but you get into a never-ending spiral. Yeah, and there is always like a root key, if you want, that would be visible on the chip. So you could be wondering, how do you solve this? Yeah, and the solution comes also from a different direction, yeah, than storing keys in memories. And that's what I'm going to talk about in the next few slides. That's also the solution that we have developed in our company, Intrinsic-ID. So a chip, physically speaking, yeah, is a completely unique physical object. And that uniqueness, yeah, you can characterize in terms of a digital information, in a digital bit stream. So you can think of this as characterizing the chip by its physical biometrics. Now, if you're able to determine that biometrics, you can create what we call a fundamental root key from the physics of the chip itself. Yeah, and that fundamental root key you can then use in all those chips, in all those IoT devices, yeah, as there are of many varieties, of course, in the market, from planes to cars to voice-assisted devices, which makes them all also immediately physically unique. And from that fundamental root key, you can derive other keys then that are being used for device authentication, for data integrity, and for data confidentiality, and of course, all kind of derived security primitives that you would like to use or that you need in your system. So the next question now becomes, okay, nice. How can we measure these physical properties? Well, one of the ways to do that is by a so-called SRAM PUF. So let me explain this concept of an SRAM PUF. So SRAM stands for SRAM, a static RAM memory on the chip, volatile memory. And PUF stands for physical unclonable function. So we are going to extract these unique physical properties of the chip from the behavior of an SRAM. And why can we do that? Well, when a chip is being built in a foundry, there is always process variations, the so-called deep submicron process variations that happen during production and that give the whole chip, and in particular also every transistor, its unique, slightly random electrical properties. You can see that at the macroscopic level, because as every semiconductor engineer knows, a transistor has a unique threshold voltage. All the threshold voltage of all transistors are close, otherwise the chip would not work, but it still is unique. Now you might think, oh, those guys are going to measure those threshold voltages and turn those into unique identifiers. Well, that would be a bit cumbersome to do. But we look at a phenomenon on the chip which depends on the difference of threshold voltages, because that gives you immediately a very stable property of the chip. And that is what happens in an SRAM. So in this picture, number 2 here, you see a very schematic overview of an SRAM cell. 2 cross-coupled inverters with a read and a write transistor. If you start up the memory, or even the whole chip, and hence the memory, every SRAM cell will choose its logical preference state, either logical 1 or logical 0, depending on the difference between the threshold voltages of the PMOS transistors in the inverters. So if you look right after startup in the memory, you see a memory filled with zeros and ones that is unique for that memory. Now, in order to make that stable over temperature and lifetime conditions, you need to develop an algorithm, that gets this completely stable. And that is what we have developed to make sure that after application of the algorithm on the uninitialized startup values, you end up with a very stable cryptographic unique device key. Very stable means always. In Phoenix, in Alaska, in 10 to 20 years from now, always the same key. Nice is that it gives you a device unique unclonable fingerprint. The entropy comes from the manufacturing process, so nobody has influence on this entropy, not the builder of the chip, not the design house, not Intrinsic-ID, and it has no key material programmed. So in that, we have turned that Intrinsic-ID into a product, a hardware product called QuidiKey that implements this key extraction from the SRAM behavior, and the software product called BK, that does basically the same. It is a software package that can extract from the SRAM behavior the unique device keys. So a little bit of detail on those products. First on QuidiKey, it's an IP block. So it's RTL, you see here on the right, it exists of an engine, an APB slave interface, and a connection to the SRAM, and a number of interfaces to other peripherals. What it does is it uses the behavior of the SRAM, as explained, to construct device unique keys, to wrap other keys, to generate random numbers. It has a built-in self-test. It offers PUF diagnostics to allow our customers during manufacturing to see the PUF behaves well. It can be built with standard SRAM, 6-transistor SRAM. It's pure digital logic, runs in a single clock domain, and comes also with driver software. So you see it's a fairly complete IP block. If you don't want to implement this as hardware on your chip, but you would like to run this on the CPU, you can also use a software package called BK. It has basically the same functionality, but runs it in software on the CPU rather than implementing it in hardware. It is secure because it offers you this no keys at rest. It gives you device unique unclonable identities, and it is also proven just as QuickKey is. It's very flexible, because it's software only, works on all MCUs, is reliable also in all process nodes, and can even be implemented on existing devices. And it comes at a low cost because basically you don't need to change or add any silicon, and gives you clearly also a fast time to market. So if you have this, let's go back to that problem that we had before of having those keys in the clear, so to speak, in the memories, and why that problem is solved. So we're going to show you how to keep secret on a chip. So here we have a chip with a CPU, with an SRAM block. We have the Intrinsic-ID IP here as an IP block, but you can imagine the same thing as a software running on that CPU over here. And technically, we also need an activation code or helper data, which we have not explained in this presentation, which we can, of course, explain in more detail, but is part of the solution. So again, an orange key needs to be stored on the device, and how can that now be protected? Well, by running the Intrinsic-ID IP, either QuickKey or BK, a device unique key, the blue key, is constructed. That blue key now can be used to encrypt this orange key. And when you switch the PUF mechanism off, the blue key, the light blue key, really disappears. It is not present on the device. So after you have executed this process, you see that you end up with a chip which has an IP block, the Intrinsic-ID IP, which does not contain any secrets, which has externally the activation code or the helper data, which also has no information about the secrets, and an encrypted orange key, which you cannot read because it is fully encrypted with a light blue key, which is not present on the device. So even if you have the best microscopes of the world, you will not be able to decrypt this and get any information about the orange key. You might say, well, this activation code, does it have to be off chip? No, of course, it could also be on chip. It doesn't matter. The important point is that it does not reveal any information about the light blue key or about the orange key. So in that way, the problem of keeping secrets on a chip has been solved in a good and adequate manner. Thank you very much.
That was an excellent presentation, Pim. I do have a few questions for you, though. First, are you introducing any overhead to the system? Are you introducing wait states or anything else that might slow the system down?
Well, of course, running the Quiddicky IP or the BK software takes a little bit of time. But so far, none of our customers basically have seen that as a problem. It runs in a very short amount of time. Clock speed these days are also, let's say, sufficiently high. So it has never caused any problem in an existing system.
Does it add anything with respect to power? Are you increasing the power that needs to be drawn from the system?
Also, that is basically negligible. Again, we are in very lightweight devices, battery operated devices. And so far, there is no, let's say, meaningful impact of this. Basically, also because these systems you only have to run a few times in the lifetime, typically of a device. So compared with all the other things that have to run on the chip, this becomes negligible.
That was Pim Toyles. He is the CEO and founder of Intrinsic-ID, and I'm Rich Nass with Open Systems Media.